So, dear friends, uh, I'll be talking about tunnel effect in this video, and what is impossible for the classical particle is possible for the quantum particle is possible for the wave packet. And what do I mean by saying so is that if I have the potential and I have the particle, and if its energy is less than that of the energy of this wall, then certainly this particle is not going to cross this wall. This is what is classical physics for the macroscopic particles. But if I do the same thing, if I go with the same thing, but in the microscopic domain where I talk about an electron, an atom, a molecule, which is basically the representation of a wave packet. Now that particle has, we will find we have it has the finite probability that it can tunnel through the wall, even though its energy is less than that of the energy of this wall. So this is what makes quantum mechanics different from that of classical mechanics. And in classical, we can have the picturization of everything, but that's not the case with quantum. As Feynman rightly said, it's weird. It's purely weird. It's not understandable completely, because at the same time, the results that we obtain from quantum mechanics, they are very much consistent with the experimental outcomes, but at the same time, they at the same time, we lack to have any state of pictorial presentation of the quantum mechanics, because quantum particles do not have, basically, they do not have trajectories. That's the important point. Now here, it's not a trajectory actually I'm showing. I'm just trying to illustrate that when we make use of quantum particles, we always find a probability for the particle of whose energy is less than that of this wall. It has a probability to be found on the other side of the wall, and this is why what we articulate is that even a particle without the energy, so without I'm trying to say it having very less amount of energy, it can pass over this potential barrier, and and may tunnel, and that tunnel is not geometrical. That it will exist on the other side of the potential barrier. So we call this thing as tunneling, that it's going to tunnel. Now, if we rightly go back to the concept where we talked about the walls, the potential walls, where we have had a finite potential. It was like this: we had a finite potential, and firstly they were assumed to be infinitely thick. As a result of that, the particle was trapped forever inside this box, uh, uh, and uh, and when this potential was made finite, even though very large, it could penetrate the walls of this potential. It could be found on the other side of the wall. It could be found in this region. It could be found in this region. So now we have a situation of the particle that strikes this potential barrier of height u, and again, we choose this. The energy of the particle that we have is, if I choose this potential to be v, we choose this energy to be less than this v, and what we find here is that barrier has, it has the finite width, and and what's going to happen, what we'll find is that the particle has it certainly has some probability, uh, not necessarily a lot of probability. It has some part of the probability, even though very very small, but not equivalent to zero, as is the case with the classical physics. So there is that stand of probability that this particle can be on the other side of the walls, uh, and uh, and emerging on the other side of these walls. Now this particle that we are considering here, it certainly lacks the energy to go over the top. So it doesn't have that much of energy to go over the top of the barrier that we have, but it can tunnel through it. It can mark a state of tunneling. So if I speak it in a way that one should not be surprised, that higher this higher the barrier height and wider it is, the less is the chance that the particle can go through it. So the point is, going higher, the probability of penetration will go down. And now what we have is, that means we have a wall kind of situation, and we have the particle, and we have the region one. And this was the region two, and this is the region three that we have demonstrated here. So what we have is, now we have a particle whose energy is less than that of this barrier, and this barrier is V. So to speak here, this tunnel effect actually it does happen, and in the case of alpha particles, if we go to the example of alpha particles, the alpha particles that we have they have energies of few mega electron volts, but these alpha particles basically they have to cross a barrier of whose height is nearly 25 to 26 mega electron volts. So here the problem is, so if we talk about the alpha particle alpha decay cannot be explained by virtue of the Newtonian mechanics, because the alpha particle should stay inside the nucleus forever, because its energy is less than that of the barrier potential of the nucleus that it has to cross. But we have alpha particles, and these alpha particles they are coming out of the nucleuses. They are crossing this barrier, and even though the probability of crossing the barrier is less, and this is this alpha decay is basically an example of quantum mechanical tunneling, and and we certainly know these alpha particles are emitted by radioactive nucleuses, and we and now the point of that probability, that the probability to cross over this barrier, this alpha particle, that the example that I chose here, that then what could be the plausible way of at least getting an idea that this alpha particle has the chances to come out of this nucleus. So if this is the nuclear wall and you have the alpha particle, what this alpha particle does is that it hits this wall 10 to the power of 34 times to 10 to the power of 38 times in just one moment, or before it has to cross over this wall. So it's the struggle. It seems to be the struggle of the alpha particle hitting the wall again and again, many more times, and and then even though its energy happens to be very less, it certainly has the probability to cross. So sooner or later it does get out of this thick wall of potential. So tunneling occurs in operations of certain semiconductors also. We have in semiconductors, we have quantum mechanical tunneling, what we call as semiconductor diodes, in which electrons pass through the potential barrier, even though their kinetic energies are smaller than that of the barrier the barrier heights that they have in front of them. So alpha particle is an example of quantum mechanical tunneling, and these semiconductor diodes where we have quantum mechanical tunneling. Now, if we assume that a beam of some identical particles, all of which have the same kinetic energy, and these this beam of particles, they are coming from this side. They're coming from this side, and they are hitting this potential. They are they are hitting this potential barrier, and this barrier has a height equal to say v, and it has a length equal to l. So on both the sides of this barrier, if we see this is the region 1 and this is the region 3rd, on the both sides, what it means is that there's no force acting on the particles, right? And so the potential or the potential in this region and the potential in this region is immediately equal to 0, because we assume that there is no force acting on these particles that are moving towards this thick wall, right? So on both the sides, this potential is 0. Now, if we think in terms of a wave function that's representing these incoming particles moving towards right, and if we have that psi 1 and then we have psi 2, say for example, that represents the reflected the reflected particles, the particles that will be reflected back, and moving to the left. Okay, and let me have some psi 3rd. So I'm just trying to make things here so correlative. If I go with, so what I have is I have a potential barrier, okay, and this barrier has a width equal to L, and this is my point where x is 0, and this is my point where x is L, and this is my psi 1, and this is my psi 2, and this is my psi 3. So this is what I'm talking. So what I'm assuming is here is that you have the particles moving, having same energies, moving towards this barrier, and there are particles that are flashed back by this barrier, and if I go on presenting this as psi 1, psi 1, psi 1a, and the reflected one as psi 1b. Okay, and then we have psi 3rd that represents the particles, the particles that have transmitted through this barrier. Now the wave function 2nd that we have here, this wave function represents the particles inside the barrier, okay, and some of which end up in the region 3rd, while the others return back to this region. So this is the psi 2 is you have the particles that are with psi 2, and which show up that some of the particles are in psi 3rd, and some of the particles are in have returned back to psi 1. Back to psi 1. Now the transmission probability for the particle to pass this barrier is equal to a fraction of the incident beam. The transmission probability. So it's the transmission that we are talking about. Now this transmission probability, suppose it's t, for the particles to pass this barrier is equal to the fraction of the incident beams that go through this barrier. This probability is calculated. This transmission probability is calculated, where we do a lot of algebra there, and we calculate this transmission probability, and the value for this transmission probability t comes out to be e to the power of, if I have this region as k1, and this is k2, and this is k3. Now this transmission probability that we calculate, this comes out to be t is equal to e to the power of minus twice k2l. So see, we are having a value for the transmission. We are dealing with a case where the energy of these particles that we have bombarded on this barrier potential is less than that of this barrier potential, and still what we have is we have the transmission probability. The electron or the particles that we are talking about here, they have a finite probability to tunnel this barrier. And the measure of that probability is given by this transmission probability, and we can think of this k2 as under root of twice m times v minus e by h cross. That's it.